Hello? Ah, it's working. Okay. It'll come through. Cool. So I suppose this is working. It's kind of an awkward situation because is there a way to set that one to also view the screen? No, but that one. Oh, awesome. Sounds good. Okay. So we have a newcomer. I'm not sure how many of the previous videos you've seen. Awesome. Cool. I will officially start the talk in about 2 minutes. And because it's mainly getting recorded because most people who should be watching this today aren't here. So, where were we? We were here. Okie dokie. Let's begin. So the thing that we last left off was this example of we were using lists as a way to build programs out of commands. And then what we were doing is we were using those lists and we were interpreting them with interpretation functions. And so we looked at this example code, and we kind of looked at it and thought, you know what? This is code that we probably want to write on the regular. So what we do is we have a bunch of operations. In this case, we call it a grammar, where file op is the grammar. We have a bunch of operations here. We have a write file, we have a read file, we have a delete file. And then we have functions that take these files and suspend them in lists. And then once we've suspended those lists, we write our program by joining a bunch of those lists together. And that gives us a really nice kind of pattern in which we can take this program that has no sorts of side effects, and we can take a function called a production interpreter, and it will take each operation itself, and it will take that operation, in this case it's a write file, and it transforms it into an operation that actually writes to the file system. In this case, read file, it takes an operation and reads from the file system, delete file, etc. And the really cool bit is that we can define a separate interpreter that will take each individual operation. Oh, wait, it's Jesus, what just happened? File op. There we go. It will, so we have this, test interpreter. It's going to take each of these file operations, and rather than actually going to the file system, it yields a map, where that map is effectively behaving like a virtual file system. And so in this case, write file, it saves some file to the map. Read file, it doesn't do anything at all. And what delete file does is it will actually null out that specific value in the virtual file system. Now, there's a couple of interesting problems with this. One, being good functional programmers we are, we don't really like doing any sort of side effects. So when we do this prod interpreter, we're actually not yielding sync, which we should have been doing previously. We're actually doing raw, uncontrolled side effects. And so we're actually not yielding that sync that we should have been expecting, because we don't actually have any value associated with that side effect. And another issue with this test interpreter is we don't actually delete anything from the file system. We null it out. And because we're using this mconcat map function that we'd used before, we're using the monoidal behavior of how map works, but we're not actually modifying that map in any sort of way. And so the really annoying part is, if you look at this function append file, we actually can't write it. Because if we look at it, we can see that this read file function doesn't actually read from the file system at all. It yields a list of operations that have yet to be executed. So we've kind of got this issue here that we can't write a function that depends on previous versions of these functions. We can only create some sort of serial list of operations. We can only sequence them in a certain order. And yeah, it's not very useful. And so I kind of left you at this. I was showing you that this is like a program that we often would like to write, but it has some issues. It's kind of useful, but it's not perfect. And I told you that what this was, this kind of pattern here of building up a list of operations into some sort of list and then interpreting it later on, is what is called a free monoid. Now we looked at monoids before. Up here, we looked at how a monoid is simply a semigroup, where a semigroup is something that has a binary operation between two separate values that also yields a value of that same type. It has also got an empty element called mempty, which is the identity element, such that, as you can see here, by combining the mempty, the identity, with any other value yields that same value. Now, when I say free monoid, the free monoid in terms of the free part of the monoid is what is the list. List is the free monoid. And I'm going to explain why that's the case. When I say free, here's a linked list. And in this linked list, it has the linked list is made up of two different types. It's either what's called the diamond type, which has a single value, and then it has a tail, which is the rest of the linked list. And the final value, the sentinel value that represents the end of the list, is called mempty. And you can see how those actually represent the two operations that we've actually defined for monoids. We have diamond, which combines, two monoids, and we have mempty, which is the identity element. And what we can do is we can define, whoops, I have lost track of what's going on. We can define this function called foldmap that traverses itself through some sort of linked list, and it has a function that converts some arbitrary type A to some sort of monoid. And it will traverse itself recursively. It will first convert the head, and then it will combine monoidically the rest of the list that has also been converted to monoids. So what we'll do, as an example, I'm going to put this microphone down for a second. Actually, no, I've written this example right here. So here's an example. We have this trait called, we have this type called nat. And so nat is a standard church encoded natural number where every natural number is one of two things. It's either a 0 or it's a successor of some other natural number. And as you can see here, we have this function called toInteger on any natural. And what it will do is it will convert that natural into an integer. So 0 converted to an integer is just, the actual 0. And successor, if we want to convert some sort of successor of some other value, it's just 1 plus what the other thing that is the successor converted to an integer. So just a standard recursive function. It'll take some natural number and squash it down to an actual integer. And so you can see here, I've got suck and 0, and I've defined a bunch of natural numbers. We've got 0, 1, 2, 3, quite easy. 3 is a successor of 2, 2 is a successor of 1, etc., etc., etc. And so what we can do is we can create this linked list that is effectively, it's a list of 3 values, 1, 2, and 3. But you can kind of see that it looks a lot like addition. It looks like I could actually write, if I wanted to, so you can kind of see that this LL is a linked list, but this thing right here is 6. So what I've done is I've almost suspended the idea of monoidically combining these values. We've taken, this would just immediately collapse itself into 6, but this one doesn't immediately collapse itself into 6. And it doesn't collapse itself into 6 immediately because 1, 2, and 3 aren't monoids. We can't convert them into a monoid yet. And what we can do is we can convert this linked list into a single value with this fold map function. Because we have explained to the fold map function, yes, we have a way to convert this linked list, this recursive data structure. We can convert the things in the recursive data structure that aren't monoids into things that are monoids, and then we can collapse it down into a single value, 6. Now, see, that was kind of interesting. What we've done is we've suspended some sort of operation. In this case, we've suspended the idea of monoidically collapsing some value. And this is the kind of practical example of that. What we've done is we've suspended the idea. We have a production, we have a production interpreter, we have a test interpreter. We've suspended the actual execution of the program. We've deferred it to some later point where we can choose whether we want a production interpretation or a test interpretation. So we know what monoids are. Monoids are just simple values that can kind of be combined in some sort of binary operation. And we've seen how monoids kind of solve our issues in terms of sequencing. We can have a single monadic value, and we can use a monadic value to depend on some of the previous value. And we can also use monadic values to suspend things like side effects. We've seen that with sync, we've seen that with state. So we're going to get to that. We're going to think. So we've got this free monoid, which is this data structure. It's a recursive data structure, and it suspends monoidic operations. Now, here's a proposal. What if we have a free monad, where a free monad is also a recursive data structure that also has a fold map function? And it's a fold map function that takes values of some arbitrary A and converts them not to monoids, but to monads. And here it is, the free monad. So you can kind of see what's going on. This is a really, really scary kind of signature. And James, I want you to respond here because I want you to tell me if this isn't being clear with this explanation. So free is made up of 3 separate values or types. These are actual like constructs, like actual pieces of data. First of all is the point. You'll notice that that matches the same function defined on the monad interface, which is point. We have flat mapped. You'll notice that is representative of the operation that we've defined on monads called flat map. So point is quite quote unquote simple. It takes some value. Oh, actually, we'll get to that in a second. I'm going to show you this example here where we're writing to the file system defined in terms of a free monad. I'll actually zoom out for a second. So here it is. Here it is in the free monad example. It looks pretty much the same. Looks pretty similar actually. We've got 3 different value types. Oh, we have 3 different values of what we call the grammar. We have write file M, we have read file M, we have delete file M. These are just basic pieces of data. We have we have these like what are called smart constructors. They take parameters. They take those parameters, they wrap it up in a corresponding piece of, like, you know, struct. And then what they do is we suspend it in free. Now remember with the example before with list, we'll go back to the list example. You'll see that we just took some sort of value and we wrapped it in a list. In order to construct something that we could combine, we could smush these lists together to build up a program. This is pretty much what the same thing is going on with free, is we're taking some sort of value and we're suspending it in the free data structure. And then rather than combining them monoidically with that little diamond that we saw before, we combine them with flat maps. So we can see here we have a free, we flat map, and then we flat map again, and then we finally map. And as you can see, we have another program. Oh, here, as you can see, append file. We can actually read file. We can, you know, read from some file system, and you'll see that all contents, if the type hint pops up, is a string. It's not a list of, you know, read file M. It's not a, actually, yeah, read file M. It's It's a free of file op m string. This is not a free of file op m string. It is a string. We saw that with monads. We saw that thing if we had a monad on the right-hand side, some f of a. On the left-hand side, when we use this for notation, this thing on the left-hand side is going to be a string. And so, sorry? So yeah, the type on the right-hand side is free of file op m string. So the monad part of this free is this. This is the monad, and then this is the A. This is the F, this is the A. And so in this example, for example, read file M, when we flat map on it, the A is going to be a string. So you can kind of see what's happened is we've been able to suspend some sort of program in some sort of, we've been able to suspend these pieces of data in a data structure that is not built to the monoid interface, it's built to the monad interface. So I'm going to show you again what fold map looked like for linked list, the free monoid. What it did is it took the head, ran this f, converted some arbitrary A type that we don't care about, we make no guarantees about, and we converted it to a monoid. And then once we had converted it to a monoid, we were able to combine it with the rest of the data structure that had also been converted. Standard recursive data structure, or recursive traversal. And you can see that when we got to the end of the list, we converted it to the empty monoid, the identity, because we were at the end of the list, we didn't really need to do anything. So what we can see is we have a kind of similar structure for fold map, but instead we're going to use a very special conversion function. So before you just saw that was an A to some M, and this is what is called a natural transformation from some G, where G stands for grammar, to some F, where that F is some monad. Now, what is interesting is you can kind of see what this squiggly boy here expands out to as a natural transformation. And so this is effectively, I'm going to write this out. I'm not going to write this out. You can see that a squiggly line from F to G is effectively a function that translates some F of A to some G of A. So what it's doing is it's preserving the inner type, but it is converting the outer structure. So for example, a function that converts some option of int to some list of integers is a natural transformation from option to list. I said that the right way around, right? Cool. So in this example, fold map, we need some sort of function that is a natural transformation from G to F, which is the same as a function that converts a GA to an F of A. The interesting part is just like fold map for the free monoid is that we make no guarantee about G. G is some generic data structure. It is not a functor, it's not an applicative, it's not a monad, it's none of those things. It's just a parameterized type. It's just some G that takes some type A. But we do convert it to an F of A where that F has to be a monad. And the reason why we do that is if we scroll back up again and we look at that fold map implementation. Where is that fold map implementation? Oh my God. It was here. I was looking at it. Yeah, fold map implementation. Given that we can take this A and convert it into a monoid, now that it is a monoid, we can monoidically combine it with the rest of the tail. This is why this has to be an F, where this F has to be a monad. Because now, in the flat map, the rarefied version of the monadic operation flat map, what we can do is we can convert our value. And now that that value has been converted, we can flat map on it with the rest of the tail of the data structure. Now that's a very scary line of code. Rest easy. There wasn't really any other way to write it because the compiler didn't really let me write it any other way. There's a very specific implementation to this. But let's actually look at what those actual values are in the free data structure. So first of all, we have point, which is defined against the monadic interface. Take some value A and it suspends it into the free G of A. So when we interpret it, we take that A and we just point the F. Yeah, we just point using the monadic definition on F. Suspend, flat mapped. Takes some monadic free G of A, and it takes another function, A free to a G of B. And you can kind of see when we look at the monadic interface on flat map, it maps directly. So a flat map, I'm not doing a very good explanation here. So a flat map on a free just adds a new flat mapped value to it. So if you take some free G of A and you flat map with some other function, what you do is you create a new free that has that original free and that function that you're flat mapping with put in it. So we're actually doing no productive work whenever we flat map on a free. You build a bigger data structure. We see the same thing when we point to free. We don't do any productive work. We just wrap it in a point. And suspend is a very special type of the free kind of data structure. This is actually an atypical implementation. This is something I've kind of cooked up myself. I never actually saw this in any of the Haskell implementations. I've only seen this in the CATS implementation and the Scala Z implementation. And so what suspend does is it takes the G, the G of A, the grammar, the thing that is not the monad, and it takes it and it also suspends it into the free implementation. And we have a interesting implementation for this where suspend, what it will do is it will take some G of A and it will use the natural transformation itself to convert that to the monad. And so now if we look at this flat map implementation once again, we can see that we're taking some free, we're converting it to the monad with this flat map implementation. We're then flat mapping on the monad. We're using the value that monad has yielded. We're then using the function that is still embedded in the actual free monad itself. And then we're converting the free that yields with another fold map to convert it, because at that point in time, if you look at what this F here is, oh God, that's a free G of A. That's not what we want. Actually, that's a lie. That's a free G of B, but Scala has actually failed to type check that properly. So that's a free G of B, and then we need to use the fold map implementation to once again convert that to a monad, where that monad is an F. So this is your F of A, and then over here, oh yeah, that was correct. Sorry, that was correctly a free G of A, and then we need to do another fold map to convert that to a monad so that this flat map works. So that was a really hairy description, and I don't expect everyone to understand that in detail, but you can kind of understand that this kind of implementation, that it is effectively a data structure that is suspending data in a format that is flat mappable once it has been converted to a monad. And so if we go back to our implementation, we can kind of see, yeah, we can write the append function because whenever we flat mapping on these frees, we're building up a bigger data structure. And then we have our program. Each of these flat maps is constantly building up flat maps and functions that we're embedding into this bigger data structure. And then right at the end, what we can do is we can write our interpreters. And so our interpreters are, as I said, they're natural transformations. And so this is an interpreter that takes a file operation and converts it into a sync, where sync is our synchronous effect monad. And what you need to be really, really careful about is that this is type preserving. So file op m, if we look up, we can see that write file m is a file op m of unit. We're saying that when we interpret this, it should yield nothing. Read file, it's a file op m of string. When we run this function, it should yield some sort of string. When we delete something, it shouldn't yield anything. And so when we do this natural transformation, we're saying that when we read a file, when we have a file op m of string, we should have a sync of string. Like if we're asking for a string, we want an operation when we convert it, when we interpret it, we want a monad that reads a string. And we can see that that also applies to our test interpreter. Now, if you remember before, we've already talked about the state monad. It's a really nice way of storing some sort of value and passing that value between computations. And so test result is some state over test state, where that is the F and there is the A. And so this itself, test result, is the monad, where test state is some map of string to string. And you can see when we convert our read file, what this is when we interpret it. That didn't work. Come on. You can see that that is a state of test state. Actually, IntelliJ hasn't really type checked that properly. But what that would be a state of test state of string. So what we've done is we've converted our file op m in here, file op m of string in this situation, to a state of string in this situation. So we've preserved the type. We've said that when we've interpreted it, you need to yield the same type, whether it's a state monad or whether it is a sync monad. We are converting it to the same type of the same type parameterizes both of those monads. And so, yeah, we construct a natural transformation. Natural transformation is a kind of specialized function. It has an apply function, apply method defined for it, so we can actually call it as a function as well. As you can see, this one yields a sync of A, and this one yields a test result of A. So file op m of A to a test result of A, this one file op m of A to a sync of A. And then what we can do is we can interpret them in much the same way that we kind of interpreted our free monads. And this will work. Take my word for this. This will actually run a pen file properly. This will actually read and write to the file system. But as you can see here, sync, this here, this prod interpreter M, is a sync of unit. It's a sync of unit because this program M was a free of unit. And then we call unsafe interpret to finally execute that sync of unit and yield some sort of value at the end. Actually, that shouldn't be like that. I wouldn't say, sorry, not yield a value, actually committed side effects. Now, once again, with our test interpreter, we have some program. It's a free of unit. We have some test interpreter here that will convert it into a state. As you can see, there it is, test result of unit. That's our state over test state of A. And then we run it with the initial state. In this case, it's a map empty. And the interesting thing is, because we're actually using a map that we can actually modify and not just, overwrite things, it means that we're quite free to delete things from the state. And so what we've done here is we've effectively built a kind of quite workable version of dependency injection. We've taken some sort of program that we actually don't know what environment it's going to run under. We don't know whether it's going to run under a test environment or a production environment. And we're able to actually see its kind of inner workings because we've built all the business logic with this free data structure that embeds monadic operations. So you're probably thinking, yeah, this is pretty dope. It's pretty useful. I'm going to use this in production. For the love of God, please do not do this. I have too much to explain as to why I don't think this is a good idea to use this in production. But unfortunately, it is something that in the Megaman team we do use free. And this is actually the most stripped down implementation I can kind of give you of free that you can actually poke around and see how it's working under the hood. Now, how did I do as an explanation here? Pretty good? No issues?
Amazing.
Oh, Daniel, you're on the call. Hell yeah. Did you have any questions, Daniel?
All good from here?
What was that?
We're good? We're good here?
Okay, awesome. Sounds good. So yeah, so free, because it's a free monad, it is itself a monad. So as you can see up here, we have functor implementation, we have a monadic implementation. We also have an applicative implementation, but we're going to get to that right about now. So hopefully everyone's understood free, but we can kind of see that it's a useful data structure. We can do some interesting things with it. And it satisfies the monadic interface. So ideally, you don't really have to care how it's working under the hood. You just effectively follow this pattern. You build your structures that you want to suspend. You write your smart constructors so you don't have to call suspend all the time. And you sequence them together into some sort of free over some sort of grammar. And then right at the end, you write your interpreters. And then, ta-da, you do that in prod, you do that in test. Nice, simple pattern that you can kind of use in lots of different places. And yeah, here's that thing I showed you before. So we have, I should have called the one for the linked list actually in concat map, but I didn't. But you can kind of see that these two functions kind of look very similar, you know? While this list of, we take some list of a grammar and we convert it to monoids, and then we flatten the whole thing down to a monoid. And for free, we take some free data structure over some grammar parameterized by some A return type. We have a natural transformation from G's to some monad, and then we flatten the whole thing down to a big fat monad. And we have to ensure that that return type is the same return type of that monad. Cool. There's an interesting kind of elegance in kind of the similarities between free monoids and free monads. Free monoids and free monads. Cool. Now, what if I told you that there is not just monads and functors? I want you to keep that in mind there for a second, because I'm gonna show you something. I'm gonna scroll past all these fun things. I want to write a credentials validator. I want to take people's username and passwords. I want to validate whether their username is correct. I want to validate whether their password is, well, not correct, but allowable. And then I want to display some sort of list of errors with those kind of credentials. And so here's this pretty much over-engineered kind of structure. We have some credentials validator. We have two methods on that credentials validator. We have a validate email. It takes an email and it yields this new type that I've kind of created called a validated. We're going to get to what the implementation of that looks like in a second. We have validate password. It takes a password, looks at the password, and it returns a validated. And you might have noticed already that there's two types of validators. We have a valid, which just, it takes some sort of email, and if it's valid, says, sweet, and it wraps it up in a valid wrapper. It says, that's awesome. If it's an invalid, it's like, I don't like that. I'm gonna wrap some sort of list of errors. And here's our valid implementation. And so validated exists in two forms. Yep. Valid is what we will call the right side. It takes some value of A and it yields a validated of some error type, and a validated. And then we have invalid that takes some error type and it yields some validated of that error type and some other type. So validate email, as you can see, the valid type is the string and the invalid type is a list of errors, where errors are strings. And let's say this type is both functor and monad. When we've seen before that there's some part of these types that is the functor and the monad part. In this case, the functor and the monad part is going to be this. So there's the F and some sort of A. And if we scroll up a bit, we can say that validated is a functor. It's a functor because we have some mapping function from some type A to some B, and it will convert a validated of some error and a value of A, and it will convert it to a validated E to some sort of, validated E to some sort of B, right? And it will take some valid value V and it will map it. But if it's invalid, we just want to say it's broken. We can't actually map over it. This isn't a valid value for you to use in any sort of way. I'm actually just going to give you an error back. So this kind of behaves much like the option that we kind of saw before, but rather than just having none on the left-hand side, we have actually like a rich kind of error. It's not just like null. It's actually like, yep, it's actually not there for reasons that I'm going to explain. So the interesting part is what we want to do is when both of these errors occur, we want to merge the lists. We want, if we have both validated email fail and we want if validated password, both return errors, we want their lists to combine. And we can say that in the case of validated, if we want their errors to combine in some sort of way, we could possibly make a requirement that the E of this validated has to be a monad, because monads are things that we can combine, right? Okay, let's scroll back up. Here's the implementation of the validated for monad. The implementation of monad for validated. Ta-da! So point, easy. We've done this before. We take some A and we wrap it up into validated. Sweet. Let's write the flat map function. Valid value. So if it's a valid value V, we run the standard F function. We've seen that before with option because we want that A here to produce some sort of new validated over here, which is the return type. Invalid. So we have this E, which is, wait, I'm going to put a restriction here. There we go. E some sort of monoid. And I'm gonna take this E and I'm gonna combine it with the next error. But I can't get the next error because I have an invalid E, but I have this function here to get the next validated. But I have an E and I need an A. I have an F here that needs an A, but I only have an E. So how do I write this function? I want to get the errors here, and I want to combine the errors with the next function. You can't write monad for validated. It can't be done. It's not possible. So we have this type that is a functor, but it's not a monad. And we're like, well, this sucks, but there is hope. There's actually this type that sits in between functor and monad in the type hierarchy, and it's called applicative. And applicative is kind of interesting in that in this kind of situation here, you'll notice that I need some sort of A to produce the next validated. And everything we've kind of seen so far is in the flat map example. We don't ever need to inspect this next type. We just get this F, and example, in this example, we get valid, we get a V, we get the V, and we push it into the F. We don't care about what the actual result is. It just pops out this other side. But in this example with validated, we actually need to inspect the next value because we want to combine the errors. To do the combination, we need that inspection of the next value. And so this is our way out. We're going to write, oh, shit. Here's the specific implementation for validated as an applicative. So with applicatives, the restriction is that to implement applicative for a validated of some error, that error has to be a semigroup, so it has to be combinable in some sort of way. We have pure for applicatives, which is analogous to the point of monads, but we also have this function called app. What app does is it takes some validated function and it takes another validated and it will fetch out the function. So in the case that we have both a validated function and a validated value, we're free to make a new validated value where that function has been applied. If we have some sort of invalid error where we were expecting a function, but we have some other validated value, we can't do anything. We wanted a function, but we didn't have it. So we have to say invalid error. If we have some valid value that on the right-hand side, whether we should have expected a value, we have to say that's an invalid error. But if we have on both sides some invalid error where we are expecting a function and some invalid value when we were expecting a value, we actually just combine the errors. And what that means is, let's actually go to the implementation of applicative itself. So applicatives, as you can, that was the specific implementation, applicative is a more general interface. And so we have this function apply. As you can see, it takes some applicative of some sort of function and some sort of value and then smushes them together. And then we have this other function called lift A2, where it takes some sort of function and it makes them work on applicatives. And we're going to see the actual specific use case of that right now. Ta-da. Here we go. We have some validated email. Oh, so this is user credentials. What it's going to do is it's going to take a username, it's going to take a password, and it will either tell you whether that is got errors or it will give you some sort of user credentials type that is proof that those values are valid. And it will take this value, validated email, that returns validated password, also returns a validated. And then we use this lift A2 function. And this lift A2 function is going to take this function, make user creds. It takes a string and returns user credentials. And it will turn it into a function that takes a validated string and a validated string and will return a validated user credentials. So we've taken a function that didn't work on applicatives, was completely ignorant of the fact that these values may or may not exist or may not be valid or might have errors associated with them. And we've taken this function and we've promoted it. We've lifted it into this context such that now it can combine valid or invalid values, in this case as strings. And now we can do something really, really cool. here we have our credentials validator that I showed you before. And we have this user credentials, and we give it us our username and our password. And it will now yield either a valid value, and in that case, if it's a valid value, we provide it to sign up, where sign up requires evidence of some valid user credentials. And if we uncomment this, we will notice that Scala gets very upset at us. Come on, give me a type error. Okay, it thinks that's overloaded for some reason. I think I might have defined it in too many places. Yes, I have. Where's the other one? Oh, well, okay. That should have shown you an error that was saying you were providing me an invalid value to a function that expected a valid. And in this case, what actually prints out in this kind of situation is it's saying, it's a list of errors saying that the username must be an email or password was shorter than 8 characters. So we've kind of seen that now we've built this value that satisfies this interface called applicative, such that we can combine errors in a certain way. It's not a monad, but it's something slightly equivalent. That's kind of cool, right? This is like a kind of useful type that you can actually use. It's probably one of the few examples that you probably use applicative in Scala at least. And you might see like a few weird functions called lift_a2, or you might see app floating around. You're like, oh, what the hell? You're probably going to want to use lift_a2 more often than not, because the alternative form of using that app function is not very nice. So yeah, this is exactly what lift_a2 is kind of doing. It's taking this function, string to string user credentials, and turning it into a validated string and a validated of string, and then returning a validated of user credentials. Cool. Now, remember how I said that applicative is an interface? Now, the really interesting part is a lot of things are applicatives. In fact, anything that is a monad also has an applicative implementation. And so all these, remember all these types that we implemented monadic implementations for, here they are for applicative. So app for an option, takes some option of some function, option of a value, and returns the applied version of that option. If you have some f and some value, return some f of a. If we don't have those things, we return none. Lists are kind of simple. We have a list of functions, and we have a list of values. And effectively, we take all the functions, and for every function in the initial list, and for every value in the other list, we apply the functions. So we're effectively doing a Cartesian product of our list of functions and our list of values. Kind of interesting. We have state implementation, in much the, we apply it as a state. We saw the scariness of the monadic implementation of state before, so I don't really want to explain this one either. We have a applicative implementation for functions. We have one for free. We have one for a bunch of stuff. So you can kind of see that there's actually very specific implementations for a lot of these applicatives. But I want to show you one that I think a lot of people might be interested in. Now, we noticed something about validated in that, where are we? Let's scroll down a bit. Where is it? Ah, yes. Here we go. You can kind of see what was going on here in that in order to compute, we needed this validated, we needed the A, and then we got that A and we passed it into the next function. So what we were effectively doing is we were sequencing these operations. We were taking some sort of A, and then we're pulling the A out of the validated, and then we're taking that A and cramming it into the next function. So to make this next validated, we need the previous A. But if you look at applicative, when we apply these two values, we have both validateds already. We haven't had to do any work to make this validated. It was given to us, pre-baked. When we did this, we validated the email, we validated the password. We did all this work to produce these values. And the function that we used, this calls apply under the hood, it had the validateds provided to it. So I want you to keep that in mind. There's nothing, if we look at the flat map, if we look at monad, right? You know, if we look at applicatives, we can see app. There's an F here and there's an F here. So, interesting. Let's keep that in mind. I want you to keep that in the back of your head when I want to show you this. Here's a function, catm. It takes a list of string and we want to read those files from the file system. And we want to return some sync, in this case, some sort of promise analog, some sync of string, where we've taken all those separate file contents and we've taken them all together and we've smushed them. Let's do it for the monadic implementation. The monadic implementation, we're going to do it not with a list initially, but we're going to do it with a tuple of 2 strings. So we're only going to read, it's a pretty shitty cat. It's only going to read from 2 files rather than an arbitrary number. So, you know, we get our first file, we get some sync of string, we flat map on it, produces a new sync of string, and then we map on it to combine both of those values together. And you've noticed that because we've flat mapped, we've gotten the first string, then we read the next file, then we get the second string, then we combine them together. There's this notion of sequencing there. Because for these flat maps to work, we have to run that first and then we continue with the next function, which is the right-hand side of the flat map function. So we're like, huh, interesting. And so here's that example. I've showed you that app function before, but I've got this new function called flip app. It's a flipped version of the function we saw before. It's the other way around. So map takes some functor of A and a function from A to B and returns a functor of B. There's our functor. We've seen our monad. We take a functor of A, and we take some A, and we return a monad of A, and we return a monad of B. So what we're doing is we're getting these 2 Fs and we're combining them to produce this F. But we've used this A to produce this F. But critically with the applicative example, we haven't done any work to produce, or we haven't needed the A to produce this F. It already exists. Because it already exists, the execution order of these can be not in sequence. Which means that if we want to do this catm such that we can read multiple files at once, we can't use monad. We have to use this very friendly applicative interface that we've kind of cooked up. So here we go. Here's us writing applicative. So I haven't really done parallelization here. I'm actually deferring out to the standard library to kind of, I'm using this future value that will be, when we run, when we create these future values, these will be committed to some sort of thread pool such that they will be executed in parallel. But what you can kind of see is, remember the sync implementation that we had from before, where when we flattened our values, what we would do is we would take our sync. If we wanted to take the sync of a sync of A, what we would do is we would suspend the following operations, and then we would do this double interpret. We would execute, and then we would execute, and then we would suspend that. to produce a sync that, when invoked, unwrapped both the syncs that were wrapped up inside of it. So there's like kind of 3 layers of functions in this kind of situation. When you have a sync inside of a sync, that's 2 layers of functions. And when you flatten it together, you have 3 layers of functions, kind of counterintuitively. The type says there's only 1 layer. There's actually 3 functions wrapped up in onions, so that when you actually execute it, it will call 2 functions so that all the computations fire at once. So that's flatten. We can kind of see what's going on with flatten. And in this situation, we have a sync inside of a sync. But I'm going to show you 2 syncs being executed at once. And we need to return a sync. And as you can see, to return a sync, we've suspended some sort of operation. And what we've suspended is the execution of 2 separate syncs. And so when we go down to our applicative implementation, we can kind of see something very, very similar happening. Oh my God. Where are you? It was here, I swear. Anyone see it? Here we go. First of all, we do our suspend because we need to return a sync at the end. So, sorry, we have some function. It's going to take some value A, we have some value B, and we have some value C. And we're going to return a new function that is going to run that function in a sync of A and a sync of B, and then finally yield a sync of C. So we're taking some sort of function and we're promoting it up to work on syncs. And in the context of this suspension, we farm out to the execution context. As you can see, when I highlight context, I can see those are the things that are going to be committed to the execution context. In this case, the thread pool. And in each separate thread, we are going to invoke one sync, and we're going to invoke the other sync. We're going to wait a little while so that the computation running on both of those threads actually executes. And then when those are both done, we run the function against both of those values. So remember how I said sync? It's synchronous, it's not asynchronous. Yes, we are blocking on both of those values in each of those separate thread pools, but we are doing them in parallel. And so when those both values have been yielded, we unblock. So there we are. Now what we can do is we have a cat applicative, not a cat monad. What we're going to do is we're going to get our both file names out. We're going to read the files. So now we have 2 computations that have not been run yet. And then we have this function called join. And it's going to take both those strings, which are these file system, like these file contents. And then we use lift A2 to take this join function and promote it to work on syncs. And then we yield a function, a value that when we call cat A does not read from the file system, but allows us to call unsafe interpret, and it will read from the file system in parallel. So there we've used the applicative instance, or the applicative interface, to kind of change the behavior of how this sync works. Now, I want you to keep that in mind, that I just said that I've used applicative to change how sync works. This is bad practice. You should not do this. Monad should not be, sync should actually be a completely independent type. It's generally not a good idea to have the monad version of sync be in sequence and the applicative version of sync to be in parallel. There should be some sort of par type. But for the purposes of this talk, I have not made that separate type, just to simplify the scope of this implementation, so that I didn't have to re-implement a bunch of stuff just to get that working. So Making sense? Awesome. Now, here's another example. Remember how I showed you all those implementations of applicatives, you know, implemented for almost every other monad that we had before? Here's an example of it working on options. As you can see, we get both of our ages, we have an add function, we promote it to work on these two options. And it is, if we look at the show implicit hints, did I click that properly? If it takes its time, you'll see that it will be pulling in the applicative instance of option such that we can use this lift A2 on both these optional values, provided that these mothers or fathers' ages actually exist. And here's the form where we've used app. So what we've done is we've taken this function that takes an integer and returns an integer. And what we've done is we've taken this map function, we've mapped it over this mother's age. So now that's an option of int to int, because the first parameter has been consumed by this add function, and then we've used app to take this option of int to int to apply it to father's age. And as you can see, here's the actual signature of app. As you can see, it takes some sort of some applicative of a function and some applicative of a value and applies them. I personally don't really like the map app pattern. I think it's really ugly. I much prefer lift A2. It's kind of hard to comprehend how map app works. But if you ever kind of see that happening, you can kind of figure out that someone's doing something with an applicative. But lift A2 is generally the one I would advise because it kind of makes it very clear what's happening. We're taking some function and we're converting it such that it will now work on applicatives. Cool. Any questions? Cool. Brilliant. How long do I have left? I have 30 minutes. So I'm going to be giving this section of the talk tomorrow at cross-pollination. So this is going to be a bit of a test run. But I want to show you something called parser combinators. Who hates regexes? Regexes, disgusting. Has anyone seen the email validation regex? It's like 400 characters. It's just like stars and brackets and pluses everywhere, and you're just like, what the hell is going on? So regexes are just kind of like this write-only kind of thing that no one really can can read after it's been done. And has anyone seen this Stack Overflow question? It's someone wanting to pass HTML with a regex. They're wanting to pass a HTML with a regex. You can't pass a HTML with a regex. Can't be done. And the part of why you can't pass a HTML with a regex is that the kind of grammar that HTML is not mathematically possible to be passed with a regex. As you can see, it's a type 2 grammar. It's a context-free grammar. And regexes can only pass regular grammars. And so the reason that's happening is when you're passing something, it's depending on previous values. You're using the previous things you've passed to make decisions about what you pass next. Regexes can't do that. They can only make decisions. They can only see something and like, okay, I'm going to do this or I'm going to do this. And at every point in time, they can make a decision, but they can't make decisions on previous values. Could someone name me a type or an interface that allows us to make decisions based on previous values? We've been talking about it for a while. It's called a monad, right? We can take some monad of A and we can map a function that takes an A and produces some new monad of B. So we've made a decision based on the value A. That's kind of interesting. What if we could, when I was saying when we want to pass something, we want to pass some value, pass some B, and we want to use previous past values of A, and then we could make a decision based on those A's to produce our passes of B's. So let's make some sort of type, some sort of parser of some type T or some type A, what do we care? Some parser type. Let's do that. Oh my God. Cool. First of all, I want to show you in a type called alternative. Alternative is quote unquote a monad on applicative functors. And it has this weird diamondy thing. And so the alternative interface kind of says that for some alternative of some arbitrary type, we can do this diamond where we could have one alternative and we have another alternative and we get to make a decision. We can choose one or the other. It's alternative. And so we can write for some F a custom implementation to define what this weird diamondy thing does. And we can define some, utility functions. We have one called many. As you can see, it takes a single function argument and repeatedly applies it until the function fails and then yields the collected results up to that point. And so function failing, I'll show you what that means. And then we have another one, sum, behaves similar, except it will fail itself if there is not at least a single match. We're going to get to that in a second. But as you can see, the kind of core of how this is working, both many and some, kind of depend on each other to actually work. Do they? Actually, no, they don't. But they kind of, alternative is built off applicative. We've needed applicative to kind of make it work. Don't really worry about the implementation here, but just remember how many and some function. Next up, here's the parser type. That's a parser. So what is a parser? A parser is it's a wrapper around a function where that function takes a string and returns a list of possible alternatives, where those possible alternatives are values of A and the rest of the input stream. The most simple example of that is item. So it's a parser of some character, and what it's going to do is it's going to take, if it's an empty stream, we return an empty list. We didn't pass anything. If it's a stream that's not empty, we get the first character. That's the thing we've passed. That's the char. That's the A. And the rest of the stream that we have yet to consume is the tail. And so when we run that, when we take the parser, we get the stream, we cram it into the function. If it spits out a result and an empty stream, it's consumed the entire stream. It's like, cool, there's your result. I got your result out. In this case, it would have been just a single character. List. If there was the rest of the stream, in this case, RS, rest of stream, the parser did not consume the entire stream, we fail with a left. If something weird happened otherwise, then we're just going to be like, oh, something disgusting happened. And the thing that is disgusting that has happened is that this list has multiple different values. And we call that an ambiguous parser. And you can write your parsing logic incorrectly such that the parser just didn't know what it was meant to pass. It might have looked at a function definition, but also thought it was a class definition. If, say, it was passing a programming language, it's gone, what the hell is this? And there's various ways in preventing ambiguous passes, but it's something that you can definitely do. And it's not the fault of the implementation, it's the fault of how you've actually written your passes. So, passes. So let's actually look at the implementations of both functor, applicative, and monad for a parser. So for a parser, implementation of map is given some input stream, run the parse function, which is going to yield a tuple of past values and new streams, and run the functions against the past values, preserving their new streams. I want you, when I'm saying streams, I'm saying that the parser could have made is passing multiple things at once. And along those multiple things at once, it may have passed different A's. And that when we are mapping over the A's, we are mapping over all the potential values it could have passed. Pure takes some value A, puts it in a list of that, that is the thing that we've passed. We're saying to make a parser of A, if you give me a value of A, I will pass it. And I will pass it by taking that stream and doing effectively nothing with it, but definitely putting that A in that list of values that we've potentially passed. Applicative. Now this is kind of interesting. You can kind of see what is happening with applicative is we're effectively sequencing values here in kind of a weird way, such that, first of all, when we have our parser, first of all, we pass some of the stream to yield the function that we have passed, and the rest of the stream we've worked our way through the actual input stream. Then we take some of that remaining input stream and we pass it into the next parser, which will yield some A. And once we have that A, we get the function we've passed and the value we've passed, we smush them together, and then we yield the rest of the input stream. Hopefully that makes sense. And you can kind of see here, it's a parser of a function and parser of some value, and we'll yield some parser of B. And here's the monadic parser, which is a bit terrifying. But you can kind of see what's happening is to build a parser, a flat map. So we have a parser of A, and we're using some A to make a decision to yield some new parser. There's the decision making that I was telling you about. What it's going to do is it's going to take some stream S. It's going to consume some of the stream to produce a new value A. It's going to take that value A and the new input stream and the new stream that has had some of it consumed. For every possible value that it has passed, we will run the function to produce the new parser, and we will push in the rest of the input stream to yield a new list of streams and values of type B that have been passed. That's our new parser. That is this return type. Hopefully everyone's read that function, that doc at the top of that function. And so those are our implementations. So, how much time do I have? I have 10 minutes. Wow, I don't really have enough time. So we're going to make a very special parser. It's the failure parser. And the failure parser takes an input stream and it passes nothing. Nothing, zilch. Pass no values, no input streams have been consumed, empty list. Here we have a combine function. Now here's that list happening. What it's going to do, if we have parser of A and another parser of A, To combine two parsers, we take their input stream, push it to both of the functions that consume that input stream, and we smush together the results they make. What option is going to do is here's option encoding the notion of failure. And remember how I said before, up here with many said many takes a single function argument and repeatedly applies it until the function fails. And you noticed I defined failure to mean empty list of that the return type of the pass function is like it's an empty list. Nothing happened. We didn't pass anything. And so you see what option does is it gets this first parser. It pushes in the S. And if the empty list pops out, we're like, well, that didn't work, did it? So then we use the next parser. We take the input stream and we push it into the next parser. Otherwise, if it was actually, if we did successfully pass something with PA, we just return whatever PA passed. Cool. So, not quite. So option corresponds to the diamond with the line through the center for alternative. So what it will do is many will take some parser and it will go parser, diamond, parser, diamond, parser, diamond, parser, diamond, parser, diamond. So it's going to continually run itself over and over and over and over again until it says, I can't pass anything anymore. Cool, alternative parser, as you can see. Diamond, option. Empty, failure. Cool, here we go. Let's start actually from a very simple function, string to a list of some type A to string, we can actually start to build up some kind of quite useful combinators. Satisfy. It's going to take, we're going to pass item. So item was parser of char. And where is it? We're going to flat map on. So if the char we passed satisfies this predicate, we're going to pass it. We're going to say, yep, I successfully passed it. Otherwise, we failed. One of. We take a list of characters. We make a new parser that will only pass values that are contained within this list. Chain L. It's going to take a parser and a parser of some operation. In this case, a binary operation. And some value A. I'm going to see what that is. And what it's going to do is it's going to repeat it. It's going to use this chain L1 function, where chain L1 passes one or more occurrences of P separated by the op and returns a value obtained by recursing until failure on the left-hand side. This is kind of a very scary function. But I want you to ignore it. But I want you to think of like, what is this type doing? It's taking some parser and it's taking some parser of some sort of operation. So maybe some sort of operation we're kind of talking about is like maybe a plus sign. What if you had 1 + 1 + 1 + 1? The thing we're passing is plus. We're going to get to that in a second. Let's do some more things. Char. This is going to pass some single character that we specify. So we use a satisfy function and we say, if that C is, if the thing that we pass is equal to C, it's a parser of a character. Spaces. If it's many, we use this one-of parser. It's a parser of one of these things. We are going to repeatedly apply this one-of parser over and over and over and over and over again until it says, no, I can't pass anymore. I've failed. And then what many will do is come on. So yeah, many returns a list of characters. Oh, sorry, a list of strings, and we use make string to collapse it all down. So spaces will pass some big fat string of white space. Alphanumeric makes sense. It's going to continue to pass things that is a letter or a digit. String. If we want to pass some sort of string, so we want this parser to succeed when we provide it foo. What it's going to do is, if it's an empty string, it will immediately succeed because it can at any point in time pass the empty string. But if it's some sort of non-empty string, first of all, we pass the first character, and then we pass a string of the rest of the rest of the string. So this will recursively pass itself over and over and over and over and over again. And so it will pass a string, and it will pass that string by incrementally consuming a single character from the stream and passing that rest of the stream along to the next character parser. Token takes a parser, passes some spaces. Reserved passes a string as a token. Digit satisfies if it's a digit, passes it. Natural, if it's some sequence of digits, collapse the string and turn it into an int. Number. Try and pass if it's got a negative out at the front, otherwise pass the empty string. And once that has happened, pass some sequence of digits. Surrounded. Takes like maybe the opening brace, passes some parser of some choice that we've made of some other parser, and then passes the closing character, or closing string, sorry. And then it yields whatever is in the middle. As you can see, it's gone reserved, then it's got the n, then it's passed the reserved, and it's yielded n. So actually, no. Better. Cool. Let's pass arithmetic. Also, while doing it, we're going to preserve order of operations. So here's Bacchus-Naur form. If you've ever done a compiler's course, you've probably looked at this before. So we've defined what digits are. You can kind of see that expressions are terms and addop, where addop is either plus or minus, and some other term where terms are either factors and mulops, and mulop is a multiplication symbol, and factors are bracketed expressions or numbers where expressions are also. So it's kind of like this recursive loop that all of these kind of productions depend on each other. And this is how you define order of operations in some sort of tree such that it makes sense. Here we go. I want you to look at this, commit it to memory, and I want you to see how literal the transcription is using parser combinators. Ta-da! So we define these things, the expression type. So add, that abstract syntax tree is made up of 4 values. It's either a literal, which is some sort of integer. It's either sub that takes 2 expressions, mul, which takes 2 expressions, and add that takes 2 expressions. When we evaluate this abstract syntax tree, we unpack the values from these data types. We evaluate A and B recursively using the operations according to the actual value that we're interpreting, and lit unpacks the value that we've passed during the parsing process when we've promoted it to the abstract syntax tree. And as you can see, at every point in time, the parser itself is actually passing that abstract syntax tree, in this case, expression. So integer, quite simple, takes a number, passes that number, puts it in lit. Expression, as you can see, expression, term, addop, term, and that brackets means repeatedly applied. Oh, sorry. It means optional. And so term, chain O1, expression, chain O1, term, addop. Term, factor, molop, where a factor is an int or surrounded bracketed expression. Factor, surrounded bracketed expression. So this is pretty much WDL transcription at this rate. So we've built this very effective domain-specific language in 400 lines. Here's add operation. It's a function that takes an expression and returns an expression, and it's the curried form of this class constructor. Same with sub. And so an add-op is either some infix operation or another infix operation where this is the constructor. And this is the constructor that we've bound to passing this token in the middle. And then apply takes our expression, takes our input stream, runs it, and then maps over the end of it an evaluation function. And we're allowed to do that because that's an either, and either is a functor. There we go. There it is. Ta-da! That's it working. So we've kind of built this very self-documenting parser that is able to parse grammars that regexes cannot parse, because regexes cannot parse recursive grammars. And we have just successfully parsed a recursive grammar. Woo! That ends this talk. If anyone has any questions. Good shit. Hell yeah. Thank you very much.